Hello everyone, my name is Fatih Abrar bin Muhammad Akhiruddin and I am from Team 1 for Mechatronics Group Project, and today we will be presenting our group project, which is the design and implementation of a mechatronic system for VGAS in gas turbine. So to start, I will be going through the background, problem statement and objectives of this project. So the project background is about gas turbines, which is the Siemens SGT 500, which are widely used in industries to generate power and drive heavy machinery. These turbines experience changing electrical loads and surrounding air temperatures throughout the day. To keep the engine running efficiently and safely, the amount of air entering the compressor must be controlled. So this is done by using variable inlet guide vanes, or also called as VIGV, which are adjustable blades located at the air intake. So the problem statement for this project is during startup or when power demand drops, a gas turbine can take in too much air relative to the fuel being burned. This can cause flameouts, wasted fuel, or dynamic compressor surge, which risk damaging the internal engine components. So to solve this, the VIGV mechanism must adjust the vane angle accurately and quickly, which is under 2 seconds, whenever power demands change. However, controlling these vanes in real plant comes with practical challenges, which are the mechanical links and vanes face heavy air resistance force during operation. And second one, the system must prevent the vanes from moving beyond their physical mechanical limits to avoid structural breakage. And if the position feedback sensor fails or loses signal, the system needs to detect the fault immediately to avoid unsafe conditions. Therefore, there is a need to design, simulate and validate a reliable PLC-based control architecture that can safely position the IGVs within the required response time. This leads to our project objectives, which is the first one is to design a complete mechatronic architecture for a Siemens SGT 500 VIGV system using an electric servo motor with gearbox, a basic PLC, and a rotary encoder, and to develop and map the PLC control strategy, including digital analog I/O allocations, ladder logic for position tracking, and the third one is to model and simulate the closed loop system using MATLAB Simulink to verify that the vane angle responds accurately within the required target time of under 2 seconds. And finally, the objective is to integrate a safety and stop interrupt and a sensor fault alarm and detection system into the PLC logic.
Thank you. My name is Raid. Now let's walk through our system architecture and component selection, starting with our closed loop block diagram at the top. So the system receives the desired angle as the set point. This set point is compared against the actual feedback to generate an error signal. Then our controller will process this error signal and sends a control signal to the brushless AC servo motor. The motor produces a drive signal that passes through a planetary gearbox to set up the torque and deliver precise rotational motion, which will drive the mechanical linkage. And the linkage physically rotating the VIGV to achieve the actual VIGV angle. Finally, the actual angle is continuously monitored and fed back to close the loop, ensuring the real-time positioning accuracy. Now moving down to our component selection and technical justifications. First, our actuation medium is the electric system. Unlike hydraulic options, electric actuation completely eliminates oil contamination risks and integrates seamlessly with our PLC control interface. Second, our final control element, we choose a brushless AC servo motor combined with planetary gearbox. This pair provides high torque delivery, exceptional positional accuracy, and long operational life due to the absence of brush wear in the motor. And then finally, for our feedback sensor, we selected a rotary encoder, which can deliver continuous, high precision angular feedback of the vane orientation to maintain accurate clock loose control. Now, I will hand it over to Shafiq to cover our I/O mapping and interface design.
Hello, my name is Muhammad Shafi Ilmi. These slides present the PLC I/O mapping of our VIGV position control system. The purpose of the I/O mapping is to define how all field device communicate with the PLC through input and output signal. On the input side, the PLC receives two analog signal and three digital signal. The analog input include AI1, which receive the desired VIGV angle from the master controller, and AI2, which receive the actual VIGV angle from the rotary encoder as a feedback. The digital input consists of HMI start-stop command along with the open limit switch and close limit switch, which are used as an stop protection to prevent the VIGV from exceeding its operating range. After processing this input signal, the PLC generate two output signal. DO1 enable the AC servo drive to move the VIGV to required position, while DO2 activate the fault alarm whenever an abnormal operating condition is detected. So overall, the PLC act as the central controller by receive all input signal, executing the control logic and sending the appropriate output command to ensure accurate and safe operation of the system. Okay, next, this slide illustrates the signal mapping and HMI interface of our PLC-based VIGV position control system. So starting from the on the left signal flow diagram, the system begin with 5 input signals sent to the PLC. The master controller provide the desired VIGV angle, while the rotary encoder continuously send the actual VIGV angle as a feedback. And HMI start-stop command and the open and close limit switch are connected as a digital input of operation and safety. The PLC process and after that the PLC process all this input signal using the programmer control logic. Based on the comparison between the desire and the actual angle, the PLC generate output command DO1 enable the servo drive to move the VIGV actuator, while DO2 activate the alarm whenever a fault condition is detected. So the rotary encoder then measure the new VIGV position and send the update angle back to the PLC. This continuous feedback create a closed loop control system allowing the accurate position control. On the as you can see on the below, this is the example of the HMI interface which allow the operator to interact with the system. The operator can start or stop the system, enter the desired VIGV angle, monitor the actual angle in the real time, and observe the system status and alarm condition. This interface will enable a simple operation while providing the continuously monitoring of the VIGV position. So overall, the PLC act as the central controller, coordinating communication between the sensor, actuator, and HMI to achieve accurate and safe VIGV position control.
Hello, my name is Muhammad Aiman bin Muhammad Salim. So this slide shows the PLC ladder diagram and the overall control logic used in the control that variable inlet cat fin and the VIGV system. The ladder program consists of 7 main rung, which each rung perform a specific function in the control sequence. So the process begins with stop latch circuit, allowing the operator to control the system through the HMI. Once the system is started, the PLC will check the end stop limit switch to ensure the servo motor can operate safely without exceeding the limits. Next, the PLC will continuously compare the desired vent angle entered by the operator with the actual angle measured by the encoder. To ensure reliable position operation, the 2-second response timer also will a timer monitors the servo movement. If the servo does not reach the target angle within the limit, the PLC identify it as a response fault. Overall, this control logic ensure the VIGV operate accurately, responds efficiently, and maintain safe operation throughout the system. Okay, this slide explains the safety and fault handling features implemented in the PLC control system to ensure reliable and safety operation of the VIGV. So first, the safety feature in the end stop interlock, which prevent the guide vane from moving beyond its mechanical limit. So when either the limit switch is activated, the servo motor is immediately disabled to prevent over travel or protect the actuator from mechanical damage. However, if the target position is not achieved within 2 seconds, the PLC identifies it as a response fault. So the servo motor will stop immediately and the alarm will start to activate to alert the operator of
the abnormal condition. As summarized in the table, under normal operation, the servo reached the target position successfully. If an stop is reached, the servo stops safely, and during a fault condition, the system generates a response fault and activates the alarm. These safety features will help to improve the reliability and protect the VIGV control system from any potential damage.
Thank you, Ayman. I will now continue by presenting the simulating model and its response. In the overall closed-loop model, the desired weight angle is compared with the actual angle. The resulting error is sent to the PD controller, which derives the simplified plan GS equals to 1 over S multiplied by S plus 4. These simplified plans combine the dominant effect of the servo, gearbox, linkage, inertia, and vane load. It makes controller analysis and tuning more manageable. Three cases were evaluated in this project. In the first case, the untuned actuator reaches the target very slowly, taking approximately 17.4 seconds after the command. In the second case, the proportional gain was set to 10.24, while the derivative gain was set to 0.48. The settling time improves to approximately 1.82 seconds, which satisfies the 2-second requirement. Finally, a pulse generator applies a 0.5 seconds disturbance at 6 seconds. The disturbance is subtracted between the controller and the plant to represent a temporary resisting load on the vane. The vane deflects by only 0.34 degree and returns to the set point approximately 1.16 seconds after the disturbance ends. After the PD controller was tuned, the model was validated using two complementary methods. One of it is root locus analysis to verify stability and time domain analysis to evaluate its response performance. The root locus analysis shows the closed loop poles at s equals to negative 2.24 plus minus j 2.285. The real parts of both poles are negative, placing them in the left half plane. This means that any oscillation will decay rather than increases, telling that the system is stable. The time domain results shows a settling time of 1.8157 seconds, providing approximately 0.18 seconds of margin below the 2-second requirement. The overshoot is 4.62%, which is within the 5% design target. The final vane angle is approximately the 30 angle, showing negligible steady-state error, confirming accurate set point tracking.
To conclude, the project successfully achieves its core objectives by delivering an optimized, practical, and energy-efficient electromechanical VIGV control system for the Siemens SGT-500 gas turbine. By integrating a basic PLC, a 415-volt electric servo motor with a precision gearbox, and a rotary encoder, the design meets the strict response requirement of under 2 seconds under continuous duty. The sustainable engineering solution not only enhances compressor operational stability and power efficiency, but also establishes a reliable safety architecture through hardwired and stop interlocks and real-time sensor fault alarms for long-term industrial impact. Thank you. That's all from us.